Hi students, this is the third session of Elasticity chapter. In this session, we are going to discuss elastic potential energy and problems. The syllabus of this session is elastic potential energy derivation in case of elongated wire, and to derive U is equal to of stress into strain, and to discuss the problems. After the completion of this session, the students will be able to know the concept of elastic potential energy, the expression for elastic potential energy, and the expression for work done per unit volume, and how to solve the problems. Then the elastic potential energy is explained as follows. When a body is deformed, work is done on the body. This work done is stored in the form of elastic potential energy. Here we consider a wire of length L, then whose upper end is fixed and the lower end is loaded with a force F. Then there is increase in the length of the wire takes place, and for a small increase in length dl, the work done on the wire is given by F into dl. If the length of the wire is increases from to small l value, then the total work done is given by W is equal to integral of F into dl, and between the limits 0 and L. Young's modulus is given by normal stress by longitudinal strain, or Q is equal to F by A whole divided by small l by capital L, where F is a force acting on the wire, A is its cross-sectional area, and small l is the increase in the length, and capital L is its original length. Then by this equation we arrive at capital F is equal to ALQ by capital L, and W is equal to integral 0 to L ALQ by capital L into dl, and A, Q, capital L are constants taken outside the integral sign. Then integral of 0 to L dl. Integration of L dl is L square by 2. Applying the limits 0 and L, we have the final equation is W is equal to of into A into Q by capital L into small l square. Then divide that small l square as L into L. Then we have W is equal to of into AQL by L into L, or W is equal to of, then we know that AQL by capital L is equal to the force F and into L as it is. Therefore here W is the elastic potential energy. It is given by of into stretching force, F is the stretching force, and L is the elongation of the wire. Therefore elastic potential energy expression is equal to of into stretching force into elongation. Then volume of the wire is given by the product of its cross-sectional area into length. It is equal to A into capital L. Then work done per unit volume is given by of into FL by AL, and it is equal to of into F by A into small l by capital L. Therefore, work done per unit volume is equal to of into F by A, as we know that it is a stress, small l by capital L is the strain. Therefore, work done by unit volume is equal to of into stress into strain. Then let us discuss the problems in the elasticity chapter. The first problem is, the question is, What force is required to stretch a steel wire of 1 square centimeter in cross-sectional area to double its length? Given Young's modulus Q is equal to 2 into 10 power 11 Newton per meter square. The solution of this problem, we have to first write down the given quantities or data. Given A is equal to 1 square centimeter, then it is equal to 10 power minus 4 square meter, and Q is equal to 2 into 10 power 11 Newton per meter square. For double the length means the increase in the length is equal to the original length. Therefore, delta L plus L is equal to 2L, or delta L is equal to L. Then the expression for Young's modulus is given by Q is equal to F by A whole divided by delta L by L, and delta L and L are same, they can be cancelled with each other. Then the remaining value is F is equal to Q into A, and Q value is 2 into 10 power 11, A is equal to 10 power minus 4. Then we have finally the force required to stretch the wire is F is equal to 2 into 10 power 7 Newton. Then the second problem, calculate the Poisson's ratio for the material. Given Q is equal to 12.25 10 power 10 Newton per meter square, and N, that is rigidity modulus, 4.55 into 10 power 10 Newton per meter square. Here Young's modulus and rigidity modulus values are given. Then the relation among the Young's modulus, rigidity modulus and sigma is given by N is equal to Q by 2 into 1 plus sigma. Then the value of sigma is given by Q by 2N minus 1. Substituting the values of Q and 2N, finally we arrive at sigma is equal to 0.346, and it has no unit because it is a ratio. Then the third problem is, a wire of 3 meter long and 6.25 10 power minus 5 meter square in cross section is found to stretch by 0.3 centimeter under a tension of 1200 kg. Then what is the Young's modulus of the material of the wire? Here the given quantities are, small l is given, L is given, the length of the wire is given, it is 3 meter. Then area of cross section is given 6.25 10 power minus 5 meter square, and the change in length is delta L is given, it is 0.3 centimeter. Then the mass attached to one end is given by 1200 kg. Then as usual, the expression for Q is equal to F by A whole divided by delta L by L. Then substituting these values, in case here F is equal to the tension M into Z, where M is the mass attached to the wire and G is acceleration due to gravity. Therefore we have Q is equal to mgL by delta L A. Then substituting these values, M is 1200 into G 9.8 into 3, then 0.3 10 power minus 2 because it is in centimeter, then convert that centimeter into meter, then 6.25 10 power minus 5. Then we have the final equation, final value is Q is equal to 18.816 10 power 10 Newton per meter square. Then the next problem is, calculate the elastic energy stored up in a wire originally 5 meter long and 10 power minus 3 meter in diameter, which has been stretched by 3 into 10 power minus 4 meter due to 10 kg. And the given quantities are, the length of the wire is given and its diameter is given, D is equal to 10 power minus 3 meter, and its change in length is, increase in the length is given, small l is equal to 3 into 10 power minus 4 meter. Then mass attached to the wire is given, it is 10 kg. Then we know the expression for elastic potential energy. It is equal to half into stretching force into elongation. Half into stretching force is given by m into g, and elongation is L. Then it is equal to half 10 into 9.8 into 3 into 10 power minus 4. Finally, we have elastic potential energy is given by 1.473 10 power minus 2 joule. The next problem is find work done per unit volume of the wire, originally 5 meters long and 1 millimeter in diameter, which has been stretched by 0.3 millimeter due to a load of 10 kg, and here the G value is given, it is equal to 3 pi. And writing all the given values, we have L is equal to 5 meter, D is 10 power minus 3 meter, radius is given by 0.5 10 power minus 3 meter, and L is 3 into 10 power minus 4 meter, and mass is 10 kg. Therefore, F is equal to m into g. M is 10, g is 3 pi. We have 10 into 3, that is 30 pi Newton. The work done per unit volume is given by half into stress into strain, and it is equal to half stress is given by F by A, strain is small l by capital A. Then substituting all these values here, and the area of cross section is given by pi r square because r is given. Then finally we have the work done per unit volume, W is equal to 3600 joule per meter cube. Then questions of this session: what is elastic potential energy? Derive the equation of elastic potential energy. Derive the equation for work done per unit volume. The reference books are Properties of Matter by D.S. Mathur, Properties of Matter by R. Murugesan, Properties of Matter by Brisler and Subramaniam, College Physics, Volume 1 by Sundarajan. Thank you.